Hi there. So we're looking at combined uncertainty using the root sum of squares, also called the propagation of errors, sometimes called the summation of quadrature. This is part 4 in a 4-part video series, the first being Sig Figs and measurement uncertainty, the second accuracy, precision, error, and percent difference, and the third being standard uncertainty and instrument tolerances. And some of the concepts covered in this third video are requisite to understanding what we're going to do in the fourth video. So if you are not familiar with standard deviation and standard uncertainty and instrument tolerances, you might want to check out that video before doing this one. In any case, links to all of these videos are found at my website, www.camrat.com. Let's get started. So in this video, we're going to quickly review systematic versus random error concept we need to be familiar with. Then we're going to look at how to combine uncertainties. That's called the propagation of uncertainties. And then we'll define ranges for population means using these uncertainties. So by way of review, from part 2 in the video series, we explained the difference between two types of experimental error. Again, systematic error called determinate error or type B error, also called one-sided error, will shift or bias results, making the final result too high or too low, but not both. The other kind of experimental error is called random error, also known as indeterminate error, type A error, also called two-sided error, and it causes measurements to fluctuate above and below a central value, and it causes both positive and negative deviations from the mean value to occur. So determinate errors often can be detected and corrected, for example by standardization or calibration, whereas random errors can be reduced but not eliminated, and they can be quantified using statistics. So I want to give some context to what I'm going to explain in this video. And I'll start right here by admitting that the determination of uncertainty in the sciences has had a long and complicated history that has lacked international agreement. Now, the currently accepted rules for evaluating and expressing uncertainties were developed in 1993, and they're detailed in a 100-page guide entitled Guide to the Expression of Uncertainties in Measurement, abbreviated GUM for short, and is now endorsed by 7 international organizations. Here's a number of acronyms, some of which you may recognize, for example ISO and IUPAC, very common. Now, the GUM methods have since been adopted by various regional metrology organizations, including another list of acronyms, and some of these you may recognize, like NIST, the NRC in Canada, ANSI, for example. And the reason for this rambling introduction is to persuade the audience that although you, like myself, the author, will likely encounter a variety of methods for evaluating uncertainty as you peruse the web or books, the methods described in this document are consistent with the current, that is 2018, internationally accepted method of GUM. So our first step is to combine uncertainties from individual measurements and calculated values to get the total uncertainty of a result. Now, in the majority of chem labs, the quantities that we will be reporting are not directly measured, but they must be calculated from other quantities, and such measurements are called indirect measurements. And the process of combining these individual uncertainties is often referred to as the propagation of error, sometimes called the summation of quadrature, and even the root sum of squares. Now, the derivations of the formulas used are complex, but the formulas themselves are reasonably straightforward. Now, you'll see many different symbols for uncertainty in use. For example, S sub r standing for the standard deviation of the result, U standing for uncertainty, standard uncertainty, uppercase D, uppercase delta in Greek for difference, epsilon, and even lowercase d in Greek, the lowercase delta. Now in this document we will use the uppercase U sub c for the combined absolute standard uncertainty of the result, and we'll use lowercase u sub a, u sub b, u sub c, and so on for the standard uncertainties of the measured values a, b, and c. And these symbols are recommended by gum. So think about this with me. I'm saying that the combined absolute uncertainty of several individual measurements should be greater than any of the individual measurements. Does that make sense? However, the combined uncertainty will not simply be the arithmetic sum of individual measurements. Why is that? Because random errors fluctuate, some positive, some negative. There will be some cancellation. Now, assuming that all the errors add in the same direction is called the range method. It estimates the maximum uncertainty. But what we want is an estimate of the most probable uncertainty. So how are we going to calculate the most probable combined absolute uncertainty? Well, let's assume that 2 volumes of liquid are poured from a beaker into one container, and to keep the mathematics simple, let's assume that each volume transferred has an absolute uncertainty of plus or minus 1 mil. For addition and subtraction, the root sum of squares statistical equation for combined uncertainty evaluates to 1.41 like so. So here for operations of addition or subtraction, the result y, the uncertainty, the combined standard absolute uncertainty of the result will be equal to the root of the sum of the squares of the individual uncertainties. And we said the individual standard uncertainties were plus or minus 1, so we simply add these, square them. We get the root of 2, which is 1.41 in this case. So this equation says that the most probable combined absolute standard uncertainty is the sum of the squares of the individual absolute uncertainties. Now, doesn't that make sense? That the combined uncertainty would be greater than the largest single uncertainty, but less than the simple sum, which would have just been 1 and 1 is 2. The most probable sum of 1.41 can also be derived in the table I'm going to show next. This table shows all the possible ways that 2 random errors of plus or minus 1 can combine and the resulting magnitude of the deviations from the mean. So remember that the errors are plus or minus 1, but I'll just represent them by these symbols, uncertainty 1 and uncertainty 2. Now it is possible that both of these uncertainties could be positive 1 and positive 1. There's only one way that can happen, so that's one combination. When that occurs, the total uncertainty, plus 1 and plus 1, would be plus 2. I'll discuss the rest of the table in just a moment. Let's look at the other possible combinations. It is possible that one uncertainty could be plus and one negative, and that can happen 2 different ways. The first one could be negative, the second one positive, or reversed as is shown here. So there are 2 possible combinations, and when that occurs, the deviation is 0 because the uncertainties will cancel. The third possibility is that both uncertainties are negative, minus u1, minus u2. That can happen 1 different way, just 1, and the total magnitude then would be negative 2. So of all the possible combinations, we see there are only 4. And I'd like for us to calculate the standard deviation using this data. So we'll take a look at the formula for standard deviation. Recall that it is the root of the sum of the squares of the deviations divided by the number of values that are averaged. So n will be the number of combinations here, and we want to get this term here, the sum of the square of the deviations. So I have the deviations, let's square them. 2 squared is 4, 0 squared is 0, negative 2 squared is plus 4, and I want the sum of these. So let's say that there's only one way that plus 4 can occur, so that the sum of that term is plus 4. There's 2 ways 0 can occur, so 2 times 0 is 0. There's one way that plus 4 can occur, so 1 times plus 4 is plus 4. And then at the bottom I have the grand total. Add up all these, the sum of the squares of the deviations will be 8. I'll put that in my formula here. 8 divided by 4 is 2, and the root of 2 is 1.41. And that's the standard deviation for these combinations. Now recall that is the very same number that's derived from the root sum of square equation from gum. This is the absolute standard uncertainty is the root of the sum of the squares of the individual uncertainties. So look at the agreement here. We're saying that the standard deviation of the combined uncertainty can be calculated from the data in the table using the standard deviation equation, and that evaluates to 1.41. And it's the same number determined by the GUM equation for absolute uncertainties over addition and subtraction. Note that it is greater than plus or minus 1. It's greater than either one of these, but less than 2 because all of the uncertainties are not simply additive. We're going to plot the relative frequency of the deviations here on the y-axis versus the actual deviations. So let's go back to our graph. Notice that there's one possible combination out of 4. That's the relative frequency of 0.25, and the deviation in that case is plus 2. So I have the point here, deviation plus 2, and the frequency is 0.25. And then 2 of 4 possible combinations gives me a relative frequency of 0.5, and in that case the deviation is 0. So this point here is 0 deviation, and the frequency is 0.5. And finally I have 1 out of 4 combinations, relative frequency of 0.25, and the deviation here is negative 2. That's this point here, negative 2 and 0.25 frequency. Now on my graph I've drawn vertical lines at plus and minus 1.41 representing the standard deviation. And this means that 68% of the area under the curve will be within plus or minus 1 standard deviation, which is plus or minus 1.41. Now if some of this is not making sense to you, probably you need to go back and watch the third video in this series that deals with standard deviation and the normal distribution. So in this table, I show all the possible ways that 4 random errors of plus or minus 1 can combine. And rather than me talking you through all of these entries, I'll let you convince yourself that these are all the possible combinations of 4 uncertainties. This is the number of ways they can occur. This is the magnitude of deviation that would result in each case. This is the square of those magnitudes, and this is the sum of the squares. And this is the relative frequency of each deviation, each type of deviation. And when you do that, you can take the formula for standard deviation, and you'll get the sum of the squares of the deviation divided by the number of values. Root of 64 over 16 is the root of 4, and that's 2.0. And again, it turns out that's exactly the same number that's calculated for the standard uncertainty of the root sum square equation, 2.0. Now I've plotted here again the relative frequency versus the deviation from the mean, and you'll notice that I have dotted lines represented at plus or minus 1 standard deviation, which is plus or minus 2.0, and this area should contain 68% of the area under the curve. So we've calculated the standard uncertainty just like the standard deviation. Enough of the proofs, let's get some practice. So when addition or subtraction are involved in a calculation, the result is a plus b or a minus b or any combination of thereof. We're saying that the combined standard absolute uncertainty is equal to the root of the sum of the squares of the individual uncertainties. For example, in a heat of reaction experiment, a student combines 100 ml of cold water with 100 ml of hot water, both from Class A 100 ml graduated cylinders. Report the total volume of water and the combined standard absolute uncertainty. So recall that the individual standard uncertainties will not be the tolerance. The tolerance is the maximum uncertainty, so we need to divide that by 3 to get the standard uncertainty. So plus or minus 1 divided by 3 is 0.33 mils each. Combining these, we'd have the root of the sum of the squares of the individuals. That works out to be plus or minus 0.47 milliliters. It's the standard absolute combined uncertainty. And I'm going to carry an extra sig fig here for a reason in a moment I'll show. So the total volume is, of course, 200.0 mils. Why 0.0? Because my standard uncertainty reported to 1 decimal place is 0.5, so I need to report my volume to 1 decimal place as well. Notice the consistency and the precision between the uncertainty and the value reported. The total volume of water would be 200.0 plus or minus 0.9 mils if we worked at the 95% confidence limit, because we'd multiply our standard uncertainty 0.47 times 1.96 and get 0.9 mils. So when we're calculating uncertainties, we retain an additional insignificant figure, a guard digit, throughout any calculations to avoid introducing any round-off errors in later calculations, but then we round off the final result to the appropriate precision. Guard digits are usually subscripted or underlined. So the combined relative uncertainty, and I haven't talked about this, but let's introduce it here. The standard relative uncertainty would simply be the absolute uncertainty, in this case 0.47, divided by the actual value, and gives me plus or minus 0.2. So what's relative uncertainty? Well, it's much the same as relative or percent error. Recall, in percent error you divide the absolute error by the true value, and if you multiply it by 100 it gives you percent, but without the 100% it's simply relative. Remember, percent is relative standard deviation. That was the absolute deviation divided by the mean. So the relative uncertainty is similar. It's just the absolute uncertainty divided by the value or result. We'll get to that soon. Another example. The volume delivered by 25 ml Class A burette is 17.88 mils. Calculate the absolute uncertainty at the 68 and 95% confidence levels. Now, since a burette must be drained to the zero mark after you fill it and before you do the titration, the tolerance uncertainty must be applied twice, once when you zero the burette and a second time when you take the final teeter. Now the tolerance reading for a 25 ml burette is plus or minus 0.03. That's the maximum uncertainty. The standard uncertainty will be 1/3 of that, which is plus or minus 0.01. So the combined absolute uncertainty of the two numbers would be the root of the sum of the squares of the individuals. That comes out to be plus or minus 0.014 mils at the 68% confidence level. So the volume would be reported as 17.88 plus or minus 0.01 mils at the 68% confidence level. If you wanted to report this at the 95% confidence level, you take your combined standard uncertainty, multiply it by 1.96, and you report plus or minus 0.03 mils. Now, just as a reminder, when you're doing analysis involving masses on a balance, you must use the tolerance twice again, because anytime you tare a balance and then take a reading, you've actually taken, in effect, two readings. The tolerance has been applied twice. Note that we've only considered the built-in uncertainty of an instrument thus far. Other random errors can be added to the calculation of combined uncertainty. Let's again ask, what is the relative uncertainty? So the relative uncertainty will be the absolute uncertainty, which we calculated to be 0.14, divided by the result, 17.8, and in this case is 0008. We don't need that for this question, but I'm introducing it here because it's needed in the next problems. All right, how about multiplication and division? Unlike addition and subtraction, where you combine absolute uncertainties, for multiplication and division, you combine relative uncertainties. So for a calculation such as this, the result y is equal to a times b, or a divided by b, or any combination thereof. The combined relative uncertainty of y, that is the absolute uncertainty divided by the value y, is equal to the root of the sum of the squares of the individual relative uncertainties. Now, if I want to calculate the absolute uncertainty directly, I could just cross multiply this result y and bring it to the right, and that will give it to me directly. Let me read this with you. The relative uncertainties, not absolute uncertainties, are combined to get the total relative uncertainty. Y is the calculated result. If I then multiply y times the relative uncertainty, you see over y, it gives the combined absolute uncertainty. So what I'm saying here, you can either calculate absolute uncertainty directly by multiplying this by y, or you could calculate the relative uncertainty using this formula and then multiply that term you see over y times y to get the absolute uncertainty. For example, 25 mils of acetic acid solution is pipetted into an E-flask and titrated using a 50 ml Class A burette with 20.22 mils of sodium hydroxide titrant with a concentration of 0.1010 plus or minus 0003 molar. Calculate the molarity of the acetic acid solution and report the standard uncertainty at the 68 and 95% confidence levels. So the foundational equation for equivalence point in an acid-base titration is that the number of moles of acid, M times V, is equal to the number of moles of hydroxide ion, M times V. I'm going to rearrange this equation and isolate the molarity of the HAC. It's equal to the molarity of the sodium hydroxide times its volume divided by the volume of acetic acid. So the molarity of the sodium hydroxide was given as 0.1010, and the volume used was 20.22 mils, divided by the volume of the acetic acid, which was 25.00 mils, and the molarity of the acetic acid is 0.0817 molar. What about its uncertainty? Well, let's take it apart. The 25 mil pipette tolerance, you have to see the tables for this, I couldn't stick it on this slide, is listed as plus or minus 0.03 mils. Well, that's the maximum uncertainty. The standard uncertainty would be 1/3 of that, which is plus or minus 0.01 mils. For the 50 mil burette, the tolerance is listed as plus or minus 0.05 mils. That again is the maximum uncertainty. We want the standard value, so we divide that by 3 and 0.017 mils. But remember, we have to consider this twice. Once for zeroing the burette and once for taking the final reading. So therefore, the absolute uncertainty on the volume delivered by the burette will be 2 times that 0.017, and the root of that is 0.024 mils. This is the absolute combined uncertainty on the teeter volume. So the combined uncertainty now on the concentration of acetic acid will be Y, that's the result, the molar concentration, which we calculated up here, 0.0817, times this term here, the root of the sum of the squares of the relative uncertainties. So for the acetic acid volume, the uncertainty was plus or minus 0.01, here was that, on a 25 ml pipette square. For the volume of the sodium hydroxide delivered from the burette, we calculated that to be plus or minus 0.024 on a volume of 20.22 mils. And then we have the uncertainty of the molarity of the sodium hydroxide, and that was just given in the problem. The uncertainty was 0003 on 0.1010. If I then take the root of the sum of the squares of these relative uncertainties and multiply it by the molarity of the acetic acid, the result itself gives me plus or minus 0026 molar. So I could then report the molarity of my acetic acid solution, 0.0817 plus or minus an absolute deviation of 0003 molar, and that's at the 68% confidence level. That is the standard uncertainty. If I then want to use the 95% confidence limit, the standard uncertainty would be 0003 times 1.96, and that works out to be 0005 if you carry the extra sig fig initially. So recall that we are calculating the uncertainty of a result based on individual values. We had 1 aliquot of acetic acid, 1 teeter of sodium hydroxide, 1 titrant molarity of sodium hydroxide. If you did replicate titrations, as you normally would and should, you would average your teeters of sodium hydroxide to obtain an average titrant volume, And from these you could obtain a standard deviation of these teeters, and you would use that as the standard uncertainty of the teeter in addition to the standard uncertainty already obtained for the sodium hydroxide based on the Pipette tolerance for any single reading. Let me illustrate. Let's say all the data was the same as before, except now you did 3 teeters, and these were the volumes. The average will keep it the same, 20.22 mils, but now we have a standard deviation on our teeter, 0.02 mils. To calculate the combined absolute uncertainty of the acetic acid solution, we'd multiply the molarity of the acetic acid solution times the root of the sum of the squares of the relative uncertainties of each term. And the first 3 are the same as before. We have here the uncertainty on delivering the 25 mils of acetic acid from the pipette. This is the uncertainty of reading the burette volume based on the tolerance of the burette itself. This is the uncertainty on the molarity of the sodium hydroxide. We don't know where it came from, but it was given to us. Presumably, it's a molarity based on replicate analysis, probably random in nature. And this final term is our new term. This will be the standard deviation or uncertainty based on our 3 titrations divided by the average teeter. Now, let's get clear that these 2 uncertainties on the sodium hydroxide are different, and they both need to be included. This uncertainty is based on the construction of the burette, its tolerance. In taking a reading, it's plus or minus so much. It's a determinate error, but since we don't know which way it is, we assume it's random. This uncertainty here is based on you. You're doing 3 titrations. Let's say you're using phenolphthalein as an indicator for the endpoint. You stop the titration at the first appearance of a permanent pale pink, and you get different values. So this is a variation based on random operations by yourself, and it's different than this, and so they're all combined together. So combining all of these relative errors together, we get 0034 times the molarity of the acetic acid will give us the absolute standard uncertainty of the acetic acid molarity as 0003 molar at the 68% confidence level. If we multiply this by 1.96, we'll get the 95% confidence level standard uncertainty on the molarity of the acetic acid solution. Let's get one more example with a multiplication and division. So density is simply mass over volume. The density of a liquid was determined by dispensing 10 mils with a 10 ml volumetric pipette into a tared flask. The balanced rate of mass of 9.10 grams. Report the density and the absolute uncertainty at the 68 and 95% confidence levels. The calculation of density is simply mass over volume. It's 0.910 grams per milliliter. I'm going to report 3 Sig Figs because that's what I see in the numerator. How about the tolerance? A 10 ml pipette tolerance from the tables is plus or minus 0.02 mils. But the tolerance is the maximum uncertainty. We want the most probable or standard uncertainty, which would be a third of that, which is plus or minus 0067 mils. Now for the electronic balance, its precision is in the second decimal place because it's reading 9.10 grams. And therefore, we have to assume a tolerance of plus or minus 1/2 the smallest division. A half of that is 0.005 grams. However, whenever you use a balance, you must consider the tolerance twice because it needs to be tared before using it. So the balanced tolerance is 0.005 grams. The absolute uncertainty, then, the standard uncertainty would be 0.005 divided by 3, or 0.017 grams, and this needs to be considered twice, as we just said. So 2 times that, the standard absolute uncertainty on the mass will be plus or minus 0.024 grams. So now the combined standard absolute uncertainty on the density will be the density times the root of the sum of the squares of the relative terms. relative uncertainties. So in the case of the mass, we said the uncertainty of the mass was 0.0024 grams on 9.10 grams squared. The uncertainty on the volume was 0.0067 mils on a 10 mil aliquot. We square that, add them together, we get combined relative uncertainty of 0.0072 times the density gives us the absolute uncertainty, combined standard uncertainty of 0.007 grams per milliliter. Now notice that this combined uncertainty has 4 decimal places. The first sig fig is in the 4th decimal place. So can we report our density to 4 decimal places? Well, yes, I believe that's valid. So I'm going to report 0.9100 plus or minus 0.007 grams. Again, I'm consistent in 1 sig fig, and these agree in their precision. Now that's at the 68% confidence level. If I want to report that at the 95% confidence level, I have to multiply this number by 1.96, and that puts me then at 0.001 grams per milliliter as the standard uncertainty, and therefore I can only report the density now to 3 sig figs, 0.910. Let's look at relative uncertainty using powers or exponents. So for y is equal to a to the x, the relative uncertainty on y is calculated from the relative uncertainty of the base a times the exponent x. Let me read it again as you look at the formulas. For y is equal to a to the x, the relative uncertainty of the result y is calculated from the relative uncertainty of the base a, there's the base, times its exponent x. Let's do a chemistry example. So the KSP is the solubility product constant. And for lithium fluoride, it would be written as the molar concentration of lithium ion times the molar concentration of fluoride ion. The literature said the value is 1.84 plus or minus 0.03 times 10 to the minus 3. So the 10 to the minus 3 applies to both the uncertainty and the value. Now the molar solubility of lithium fluoride will be KSP to the 1/2. Now if that's not clear to you, I'll leave that to your chemistry prof to explain, but I just want you to go through the mathematics. I want you to take the square root of KSP and calculate the molar solubility and then report the uncertainty. We're going to use this rule. So calculate the molar solubility of lithium fluoride and report its absolute uncertainty. So the molar solubility of lithium fluoride is simply, as we said, KSP to the 1/2. So it's the square root of 1.84 times 10 to the minus 3 is 0.0429 molar. What about the uncertainty? So again, look at the formula. The relative uncertainty of the result, which will be the molar solubility of the lithium fluoride, is equal to the exponent times the relative uncertainty of the KSP, whatever was taken to the base A. So I want to rearrange this formula slightly. Let's bring the concentration of lithium fluoride to the right side, and we'll have the absolute standard uncertainty of the molar concentration of lithium fluoride will be equal to the concentration of lithium fluoride times the exponent times the relative uncertainty of the KSP. We'll put some numbers in here. 0.0429 is the molar concentration of lithium fluoride times the exponent, a square root is an exponent of 1/2, times the relative uncertainty of the KSP. It was plus or minus 0.03 on 1.84, and that works out to be 0.004 molar, standard uncertainty of the molar solubility of lithium fluoride. And so we would report the molar concentration or solubility is 0.0429 plus or minus 0.004 molar at the 68% confidence level. Now notice again the consistency. I have only 1 sig fig in my uncertainty, and it's in the 4th decimal place, so I report my molarity to the 4th decimal place. And that's it. Now I want you to note that there is a difference in the error propagation that occurs when you raise a number to a power versus multiplication or division. And you may have noticed that because they have different formulas. Intuitively, it's not obvious. So let's compare 4.0 plus or minus 0.3 squared versus 4.0 plus or minus 0.3 times 4.0 plus or minus 0.3. Now, clearly the result is the same in both cases. 4.0 squared will be 16.0, and 4.0 times 4.0 is 16.0. So you might think, well, the errors should be the same, but they're not. Let's put them in the formulas and see that. So in the case of a exponent or power here, the relative uncertainty of the result will be equal to the exponent x times the relative uncertainty of the base. So when we're squaring, that'll be 2 times the relative uncertainty on the base, which is 0.3 over 4. You work that out, that's plus or minus 0.15, and that's the relative uncertainty on the result on 16.0. And if we want to know the standard absolute uncertainty, I'd multiply the relative uncertainty times the value. 16 times 0.15 is plus or minus 2.4. And I realize that I'm going to keep an extra sig fig in this uncertainty. I know we should round to 1. We should report plus or minus 3, and this would be 16. But I want to show the difference to the other calculation. This time, let's do it by a multiplication. So 4.0 plus or minus 0.3 times 4.0 plus or minus 0.3. Again, the result is the same, 16.0. But what about the uncertainty? Well, for multiplication and division, the relative uncertainty of the result is equal to the root of the sum of the squares of the relative uncertainties. The relative uncertainties are 0.3 over 4. We have that twice. And the result works out to be 0.11, which you can see is easily different than plus or minus 0.5. It's less in the case of multiplication than it is for powers. If I then want to convert the relative uncertainty to the absolute uncertainty, I simply multiply that by the result and find out that's plus or minus 1.8, which is less than you obtain with the power. So you can see it's different, but why is it different? Well, in multiplication and division, two independent errors are being combined. And we spoke before about the fact that when you combine independent random errors, some cancellation occurs. And that was in video number 3. And that's what's happening here. There's some cancellation. As a result, for multiplication, the value is a little less than squaring. With powers, the same error is repeated x times. There is no cancellation. And hence, you'll see that the relative error with multiplication and division will be less than it will be with powers. So this is the last mathematical operation for which we're going to study uncertainties. That would be logs and antilogs. I'm going to only discuss the base 10 logs and antilogs. I'll leave the Naperian base to you. They're pretty straightforward to use. So for the logarithm of the number a, y then becomes a logarithm. And we're told that the absolute uncertainty of the log value, y, is equal to 4.4343 times the relative uncertainty of the number a. Interesting, we're switching between absolute uncertainty to relative uncertainty. And this is akin to what we saw in the rules for Sig Figs, where we saw that the absolute, if you will, uncertainty, or the number of decimal places to keep in a log value, was related to the relative, if you will, uncertainty. That would be the number of Sig Figs in the number. It works about the same way. In the case of an antilog, y equals 10 to the a. In this case, a would be a logarithm, not a number, and y now is a number, not a logarithm. So it turns out that the relative uncertainty of the number y is equal to 2.303 times the absolute uncertainty of the logarithm a. Let's try an example in chemistry. pH is the negative log of the hydrogen ion concentration, and the hydrogen ion concentration is the negative antilog of the pH. Let's calculate the pH and its standard absolute uncertainty of a solution with a hydrogen ion concentration equal to 4.0 plus or minus 0.2 times 10 to the minus 8. We'll also calculate the upper and lower limits defined by the standard uncertainty, and then we'll explain what this means. So we can get the pH first. So pH is simply the negative log of the hydrogen ion concentration. That works out to be 7.40. Now, how many sig figs, how many decimals do we keep? Well, remember, this is a logarithm. We're going to keep 2 decimal places in the mantissa because the number has 2 sig figs. Now, the rules that we're studying now take precedence over these sig fig rules, but let's see how this holds up. So for the uncertainty, the absolute uncertainty in the pH, which is this number y, there it is, the absolute uncertainty is equal to 0.4343 times the relative uncertainty of the number, which is the hydrogen ion concentration. So here's 0.4343 times the relative uncertainty of the hydrogen ion concentration. So there's the calculation. Here it's plus or minus 0.2 on 4. That works out to be plus or minus 0.02 pH units. And notice this uncertainty has just 1 sig fig in it, and that's correct. And it's in the second decimal place. That means that keeping the second decimal place in the pH is correct. So in this case, the sig figs do agree with this rules for uncertainties, which again, I want to say take precedence. This is at the 68% confidence level. So we can say that the upper pH limit will be 7.40 plus the standard uncertainty, 0.02, that's 7.42. We can write the lower pH limit as 7.40 minus the standard uncertainty, and that's 7.38. So the upper and lower limits identify a pH range, 7.38 to 7.42, in which the pH will fall within a 68% probability, meaning 68 out of 100 measurements. So this is one last problem involving logs and antilogs. In the last slide, I gave you a problem involving the hydrogen ion concentration and asked you to calculate a pH. But this time, I'll give you some pHs and ask you to calculate the hydrogen ion concentration. So let's calculate the hydrogen ion concentration, and it's 68 and 95% uncertainty in a solution whose pH was measured 3 times, and these are the pH values. I want you to state the upper and lower limits of the hydrogen ion concentration at the 95% confidence limit, and the range of pH values this includes. So first of all, we need to get the average pH of these values. It's 2.38. I'm going to carry 3 sig figs, the same as my individual values. The standard deviation works out to be 0.0351. And what should I carry here? Well, my first digit in my standard deviation is in the hundredths column. That's where it's significant, and that's consistent with the decimal position in my pH unit. So the hydrogen ion concentration is 10 to the minus pH, and that's 0.00414. Now, how many digits do I carry here? Well, in fact, I'm going to carry 2 sig figs in my number because my pH has 2 digits to the right of the decimal in the mantissa. Now, the relative uncertainty up here, the relative uncertainty of the hydrogen ion concentration, that's the number y, is equal to 2.303 times the absolute uncertainty of this exponent, which is the pH. So let's rearrange this a little bit. I'm going to take this hydrogen ion concentration and bring it over here. I'll have the absolute standard uncertainty of the hydrogen ion concentration will be equal to the hydrogen ion concentration times 2.303 times the absolute uncertainty of the pH as per this equation. Putting some numbers in, 0.0414 times 2.303 times 0.0351 gives me an absolute standard uncertainty of 3033. Now, the first significant digit is a 3, and so that's in the 4th decimal place, and look, that's consistent with my molarity, which has values up to the 4th decimal place. So the hydrogen ion concentration can be reported as 0041 plus or minus 0.003 at the 68% confidence level. And if I want to move to the 95% confidence level, I simply multiply this number 0003 times 1.96, and I report 0007. So the hydrogen ion range would be 0041 minus the standard uncertainty, the expanded uncertainty, up to 0041 plus 0007, the expanded uncertainty, which gives me a range of 0034 to 0048 molar. One last calculation, error propagation in mixed calculations. Many chemical calculations involve a combination of mathematical operations. The propagation of uncertainty can be calculated by treating each operation separately. Just remember to follow the order of mathematical operations. So here's an example. The concentration of potassium ion is measured in water samples using flame atomic absorption spectroscopy. So a set of standards containing known concentrations of potassium are run first, and they obtain a calibration curve of absorbance versus concentration, like this. So if I have standards containing 0.5, 1, 1.5, 2, and 2.5 milligrams per liter potassium, I measure the absorbances for each, and I plot them in Excel. So the data plotted using Excel's regression tool will give us the equation of the line, here's that line, along with the standard uncertainties of the slope and intercept. Then the absorbance of the water sample is measured. Its potassium ion concentration can be calculated by substituting the absorbance into the regression equation. Here's the equation of the straight line as y equals mx plus b. In this case, y is the absorbance, and m is the slope, which is given as 0.246. X is the concentration we're going to solve for, and b is the y-intercept, 008 here. So given a slope of 0.246 plus or minus 0.005, and Excel's regression tool will give you this value, and an intercept of 0.008 plus or minus 003, and Excel's regression tool will give you this as well, and an absorbance of 0.420, and the instrument, the spectrometer, will tell you the standard deviation on the absorbance. You get that as well from the instrument. We can calculate the concentration of potassium in milligrams per liter, its absolute standard deviation, and the range of concentrations at the 95% confidence level. So first let's solve for the concentration that corresponds to an absorbance of 0.42. So I'm rearranging this equation, y equals mx plus b, solving for x is equal to y minus b over m. Remember, y is the absorbance, b is the intercept, and m is the slope. I substitute my values for absorbance, 0.42, intercept, 008, and slope of 0.246, and you can calculate 1.69 milligrams per liter of potassium ion. Let's look at the graph. So a concentration of 1.69 or 1.7 milligrams per liter corresponds to an absorbance of about 0.42. So certainly it looks correct. And it's in the middle of our graph, which is always a good thing. Okay, to calculate the uncertainty, we first need to calculate the uncertainty of the numerator, and these two numbers are subtracted. For addition and subtraction, we calculate the absolute uncertainty of the numerator as the root of the sum of the squares of the individual uncertainties, the individual uncertainty on the absorbance and the intercept. These values are 007 on the absorbance and 0003 on the intercept. We combine those and get 0076. Next, we want to calculate the relative uncertainty on the concentration. We do that because this next operation is division. So the relative uncertainty of the concentration will be equal to the root of the sum of the squares of the relative uncertainties of the numerator and the denominator. So I'm going to rearrange this equation right now. I'm going to bring x to the right hand side, which is 1.69, and multiply by the root of the sum of the squares of the relative uncertainties of the numerator, which we calculated here as 0076, on 0.412. Now the 0.412 is 0.42 minus 008, plus the relative uncertainty on the slope was 005 on 0.246. Now remember, I'm multiplying by the 1.69, so I will get not the relative uncertainty, but I'll get the absolute uncertainty on the concentration, which turns out to be 0.046. I should carry only one sig fig in my uncertainty, but I'll carry a guard digit as well. Thus, the concentration I can report as 1.69 plus or minus 0.05, but I'm going to say 0.046 because this is at the 68% confidence level. I want to calculate it at the 95% confidence level, so I'll multiply 0.046 times 1.69 and say it's 0.09 plus or minus on the 1.69 milligrams per liter potassium concentration. So the range of values is 1.69 plus or minus 0.09, and this gives me a range of 1.60 to 1.78 milligrams per liter potassium at the 95% confidence level. Now, looking at that, just given the uncertainty, the range from 1.6 to 1.8 almost, I would report to my client a number of 1.7 plus or minus 0.1 milligrams per liter at the 95% confidence level. Well, given the complexity of determining a result's uncertainty when several measurements are involved, it's fair to ask if there's good reason for making the effort, and it's a fair bit of effort. But there are some benefits. Uncertainty calculations help us find ways to improve results. Often one finds that some errors are relatively insignificant, whereas others are seen to be dominant. So efforts to improve precision can be focused on the errors that cause the greatest uncertainty. Uncertainty calculations allow us to compare the precision of alternate methods for analysis of a given analyte. And uncertainty calculations give guidance in the number of Sig Figs, or the precision that a result can reasonably be assigned, and a range in which the true value is likely to be found. So let's summarize. In this chapter, we've looked at how to use these various formulas for error propagation, and they are used to estimate the most probable combined standard uncertainty for random or indeterminate errors. What about systematic or determinate errors? Well, if we don't know the direction of the bias, which is typically the case, we can consider them random, and they are included then in the calculations of the combined uncertainty. So you've just completed Combined Uncertainty, the Propagation of Error, Part 4 in this 4-part video series. And of course, I must mention that the links to the other 3 parts, Part 1, Sig Figs and Measurement Uncertainty, Part 2, Accuracy, Precision, Error, and Percent Difference, Part 3, Standard Uncertainty and Instrument Tolerance, and other chem videos, all these links are posted on the website www.chemrot.com, and thanks for watching.